Alright guys, so now we're going to move on to the fill-in-the-blank portion of the notes. And this is basically just kind of an idea. It says that the parametric representations of a curve are not unique. So I'm just going to write that. And there are infinitely many ways a curve can be parametrically represented. So what that means is that, let's say this is my curve. There's not only one parametric equation that can be made from this, because there are so many different points on the curve, each of them would have a unique kind of way to write a parametric equation. So, some might repeat, there are a lot of different possibilities. That's basically what this is trying to tell you. And you can derive parametric equations from a rectangular equation. So, as we've kind of mentioned earlier, rectangular equations are the equations we know, we recognize, and we've worked with. The y equals f of something, those normal, easy to graph equations. Now, the examples that we've done earlier have been we receive the parametric equations and we find the rectangular equation through that. So this is essentially working backwards. We get the rectangular equation and we have to solve for the parametric equation using it. So it typically follows this rule. It says that, let me find a highlighter. Okay. It says that if y equals f of x with domain x, which this is the rectangular equation format usually, then x equals t, y equals f of t for t and x. So basically, what this has done is it's incorporated the parameter that we know as t. We've kind of gotten comfortable with that already. We know that t in parametric equations is the third variable that's taken into account for both the x and both the y, so this does make sense. We know that if we had the t in our old examples, if you remember making a table with the t and then the x and the y depend on what t is. So it makes sense that you would plug in the t for the x, just as you would in any other example, which is how they got this. You would plug in the same thing, x equals t, whatever that is, for t and x. Now, what that means is the domain is x. Let's say the domain is like 0 to 5 or something. That basically means that this is like where we're working in, and that would be the t as well because it's the parameter. That's kind of where we can work, if that makes sense. Like our limit, if you will. Now let's look at this example. It says, give two parametric representations for the parabola y equals x minus 2 squared plus 1. So let's look at the parts that we need when we're working with a rectangular equation. So this is our rectangular equation. What do we need? We need the domain x. What's the domain of this? It doesn't tell us, but if you look at it, just kind of look at like, what can't x be? So we know that any number can go into this and have a solution. So that means that the domain is negative infinity to infinity. Okay, so now that we have that, we know that the kind of pattern that it follows would be y equals f of t and x equals t for t and x. So here's our t and x. T would equal negative infinity to infinity. Okay, now let's move on to y equals f of t. So basically what it is we're going to find the variable that we're replacing with t, and we're going to put t in its place. So if our formula is y equals x minus 2 squared plus 1, what's the variable here? It's x. So all we're going to do is replace it with t. Okay, so that's the y part. We have the t part. Now all we need is the x part. So x equals just t. We don't know what just t is, but we can solve for it with this. Sorry, my phone died, so I think the setup changed. I don't know, I don't really care. Anyway, so, okay, so yeah, as I was saying, we know that y equals f of t. We replaced x with t, so we're good on that. And we know that x equals t. Now you can go through all the trouble of just solving for t through this and whatever and plugging it in. That was what it would be, but you can just leave it for simplicity's sake as x equals t, y equals t minus 2 to the power of 2 plus 1, and then t in negative infinity to infinity. Okay, we're good. Alright, so this matches this setup, and it's pretty much just, using this to make it as simple as possible for yourself for finding this. But this is only one parametric representation, because the parametric representation has the t, it has the x, and it has the y. So we need to find a completely other way to write it. So basically, in the first one we decided what our variable x would be. Whatever we decide that our variable is, that's what's getting replaced by t. And that's basically what determines the parametric equation that we find. So in our first example, we said, oh, this is our t, right? So if we want a different equation, we can't use the same variable because then it'd just be the same equation. So this time we're going to switch it up and we're going to say this entire thing is our t. So we know that the domain is still negative infinity to infinity because it's still the same equation. So t is still in negative infinity to infinity. Okay, so now we show that y equals f of t instead of f of x. So if this is our variable, we just replace it. So our new y formula is t squared plus 1. So do you see what we did there? We said that this is our t, so we replaced it entirely with just the variable t because that's basically what it is. Okay, ignore that. I'm sorry, I made a mistake. Anyway, so yeah, we said x equals t, but we can even kind of define it further, because we know what t is. So if we just wanted to rewrite it, what does t equal? It equals this. It doesn't equal x anymore. It equals x minus 2 now. So x minus 2 equals t. This is like the chunk that we took. So that's basically how we're going to rewrite it. So that means that x equals t plus 2. And that's our new set of parametric equations for the second representation. And this pen sucks, but yep, that's it.